Light is the universe's language, written in photons that carry meaning across space and time. Every sunset and every screen glow is a sentence in that language. This video unlocks how to read the code, from the glow of a distant galaxy to the tiny photons powering your phone, so you can see the story light tells about matter, motion, and memory. You'll learn how color, brightness, and timing reveal history, chemistry, and the structure of the cosmos, and how this same code steers technology, medicine, and exploration. Join me as we translate the glow that binds everything and discover what light can teach us about the nature of reality. Light as the universal language of nature. Light is electromagnetic radiation that travels through space and interacts with matter, and our eyes translate a band of it into color and form. In vacuum, it races at about 299,792 kilometers per second. Each photon carries energy proportional to its frequency, a relationship captured by E equals HF that lets scientists predict how light will energize or excite atoms. When light encounters a material, it can be absorbed, reflected, scattered, or transmitted, and those outcomes carry information about the material structure. In nature, light is not mere illumination. It is a language that communicates energy, structure, and change. The sun acts as a cooperative broadcaster, sending a continuous stream of photons that drive photosynthesis in plants, guide animal behavior, and reveal the presence of distant worlds. By listening to light, researchers learn about composition, temperature, and motion across scales from leaf to galaxy. Color arises when materials interact with specific wavelengths while others are absorbed or reflected. Chlorophyll in plants absorbs red and blue light and reflects green, shaping the way leaves look. Bioluminescence in the deep sea uses chemical reactions to emit light without heat. In bright sunlit environments, polarized light can guide navigation for certain species and help some insects locate flowers. The sky's blue is the result of scattering, not the color of the light itself. Many animals tune their senses to light cycles, aligning feeding and reproduction with dawn and dusk. Spectroscopy deciphers light to reveal chemical composition. Fiber optics use total internal reflection to carry pulses of light across continents with low loss. Wavelengths around 1350 nanometers are standard in telecom due to minimal attenuation in silica fibers. Solar cells convert sunlight directly into electricity, powering devices and grids. Lasers and LEDs enable precise surgery, high-speed data transfer, and immersive displays. LiDAR uses pulsed light to map environments with centimeter-scale accuracy. Light functions as a universal code that links micro and macro scales, from enzymes harvesting photons to galaxies emitting spectral fingerprints. In research and daily life, reading light means reading information. Modern imaging, energy, and communications depend on translating that code into useful signals. The practice invites humility and curiosity. As we refine technologies and deepen our observations, light continues to reveal nature's patterns with increasing clarity. Photons as information carriers. Light travels at roughly 299,792 kilometers per second in a vacuum, making photons natural information carriers that can transmit signals across vast distances in fractions of a second. Photons are the quanta of light. In communication and sensing, information is encoded in the photon's properties, its polarization, phase, timing, and frequency, each acting as a channel for a symbol. A single pulse can represent a bit or a more complex pattern. In fiber networks, the language of photons becomes practical, as pulses of light surge through glass strands that guide them with minimal loss and interference. Beyond classical bits, photons can carry quantum information, where a qubit exists in superposition between 0 and 1. Polarization is a common encoding. Time-bin and path encodings exploit arrival time and spatial routes to define quantum states that survive noisy channels. Entangled photon pairs offer correlations that defy simple classical explanations. Sources based on nonlinear crystals or quantum dots emit single photons or entangled pairs, enabling protocols such as quantum key distribution that aim for security grounded in physics. Detectors convert photons back into readable information with varying efficiency and dark counts, shaping the fidelity of communication. Optical fibers and free space links form the two main highways for photonics. In data centers and other high-performance settings, photonic integrated circuits route light with minimal latency and power, while fiber and free space links manage dispersion and noise. Quantum channels face distinct challenges like loss and decoherence. Visible light communications, or Li-Fi, demonstrates how everyday illumination can carry data, offering high bandwidth in indoor environments while remaining compatible with human perception. Viewed as a universal code, photons translate physical states into information that scientists decode to learn about weather, medicine, navigation, and the cosmos. Spectral fingerprints tell us what objects are made of. In astronomy, photons from distant galaxies arrive with polarization, phase, and timing patterns that encode clues about magnetic fields, motion, and the history of light across space. The same language underpins modern technology, from sensors and smartphones to secure communication networks. As research advances, new photon-based architectures promise even greater capacity and resilience, turning light into a flexible, ubiquitous medium for both information and understanding of the universe. Reading light, instruments, and methods. Light carries information about the world around us by way of photons that interact with matter. When we read that information, we translate light into measurable signals. Instruments act as bridges between the fast, subtle language of photons and the slow, deliberate language of numbers. A spectrometer, for example, separates light into its constituent wavelengths with a dispersive element like a prism or a diffraction grating, revealing a spectrum that acts like a barcode for a source. Detectors then convert photons into electrical signals that can be recorded, analyzed, and compared. A telescope feeds collected light to a spectrograph, where spectral fingerprints emerge for composition, temperature, and motion. The goal is to translate the inferences carried by light into reliable, interpretable data. Absorption, emission, and scattering describe three fundamental ways light carries information about a material. In absorption measurements, a sample reduces the intensity of certain wavelengths, leaving a characteristic trough in the spectrum. In emission measurements, excited atoms release photons at specific energies, creating bright lines that reveal identity and environment. Fluorescence methods exploit a lag between excitation and emission to improve sensitivity. Imaging spectroscopy couples spatial information with spectral information, producing a data cube that shows how chemistry changes across a scene. Calibration uses standard light sources, flat field corrections, and wavelength references to ensure that the signal reflects the observed object rather than the instrument. Techniques like Raman spectroscopy and FTIR probe molecular structure by how light scatters or vibrates tissues and materials. Instruments span a broad range from simple photodiodes to complex integral field spectrographs. Detectors such as CCDs and CMOS sensors capture photons with high efficiency, while specialized detectors like photomultiplier tubes and avalanche photodiodes provide fast responses and high sensitivity. Metallic or dielectric coatings tune mirror and grating performance, shaping throughput and spectral resolution. For ultraviolet and visible light, detectors often require cooling to reduce noise. For infrared, different materials like NGAS or HGCDT extend sensitivity into longer wavelengths. The dispersive approach relies on gratings or prisms, while Fourier transform methods, including FTIR, summarize entire spectra in a time-domain measurement transformed into frequency information. Interferometers, by producing interference patterns, can resolve fine spectral structure or tiny wavelength shifts that reveal precise conditions in a sample. Imaging modalities may include hyperspectral cameras that map wavelength across a scene or adaptive optics systems that sharpen images by correcting atmospheric distortion, allowing faint spectral features to emerge. In practice, reading light means choosing the right tool for the question. A chemist might use UV-vis spectroscopy to estimate concentration and monitor reaction progress. A mineralogist could employ Raman spectroscopy to identify crystalline structures without destroying the sample. An astronomer relies on high-resolution spectroscopy to infer chemical abundances and velocity fields in distant objects. A materials scientist may apply LIBS to determine elemental composition in a quick scan of a surface. Across disciplines, data pipelines convert raw signals into spectra, then into physical quantities with calibration curves, background subtraction, and noise modeling. The result is a language that decodes light into stories about materials, processes, and places where conditions push photons to reveal their secrets. Light across scales, from quantum to cosmos. Light travels at about 299,792 kilometers per second in vacuum. In quantum terms, light comes in discrete packets called photons, each carrying energy proportional to its frequency. But light is also a wave, capable of interference and diffraction. This dual nature is the bedrock of modern optics and every imaging technique. A simple laser beam is highly coherent and can be focused to tiny spots. A hologram records the phase relationships between light waves. In information terms, E equals hf sets the energy scale for each photon. At the quantum scale, light becomes a carrier of information. Single photon sources and detectors enable quantum communication and experiments that test the limits of measurement. Quantum key distribution uses the polarization or phase of photons to establish secure keys between parties. Entanglement links distant particles in correlations that persist even when they are separated by space. Optical fibers guide photons efficiently via total internal reflection, enabling long-distance networks and data transfer. In the lab, devices like Mach-Zehnder interferometers demonstrate precise control of phase and high-visibility interference, showing how delicate light-based signals can be manipulated for metrology and computation. On astronomical scales, light is a messenger from the cosmos. Visible and infrared light reveals stellar temperatures and chemical compositions through spectral lines, while the same principles apply to nebulae, comets, and exoplanet atmospheres. The cosmic microwave background provides a near-uniform glow with tiny fluctuations that encode information about the early universe and its large-scale structure. Cosmological redshift stretches light from distant galaxies, offering a map of how the universe expands. Gravitational lensing bends light around massive objects, magnifying and distorting distant sources to reveal dark matter distributions and hidden structures. High-energy light from accretion disks and relativistic jets around compact objects exposes extreme gravity and magnetic fields in action. To read light across scales, we deploy a suite of instruments that translate photons into data. Spectrographs disperse light to reveal spectra and identify chemical fingerprints. Polarimeters measure the orientation of light's electric field to infer magnetic environments. Interferometers combine beams to extract phase information and achieve exquisite angular resolution. Radio, optical, and 10th ray observatories sample different slices of the spectrum, each revealing unique physical processes. Light also carries environmental information on Earth, with spectral fingerprints diagnosing atmospheric composition and pollution. As a universal code, light links the quantum to the cosmic, a dynamic language through which nature communicates its rules and histories. The practical takeaway is that light is not just illumination. It is a probe, a tool, and a story about how the universe works. Implications for science and reality. Light travels through the cosmos at about 299,792 kilometers per second in a vacuum, a speed that sets the tempo for how information moves and how causality unfolds, a notion echoed in a Sveti Kodi Mirazdanya. That speed is a constant. Photons, the quanta of light, act as carriers of energy and information, varying absorption and emission fingerprints that reveal the composition and state of distant objects. Spectroscopy reads these fingerprints. By tracing the spectra of stars and galaxies, scientists deduce chemical abundances, temperatures, and motion, using shifts in wavelength as labels for how matter moves and evolves. The same principle underpins exoplanet atmospheres. Quantum optics shows that light behaves as both wave and particle, a duality that constrains how precise measurements can be and defines the limits of information extraction from a system. This is not abstract math. In cosmology, light carries the imprint of the early universe. Features such as the cosmic microwave background polarization map the conditions that prevailed when photons last scattered. Observing redshift tells us galaxies recede. Because light propagates through space-time, any distortion or bending by gravity, gravitational lensing, rewrites the apparent shape and brightness of distant sources, providing clues about mass distribution and the geometry of the cosmos. Light encodes geometry. In laboratories, lasers and interferometry turn light into precision tools that probe the smallest scales of matter and the faintest ripples of spacetime. Engineering then translates these insights into everyday devices. Technologies like fiber optic communication and optical coherence tomography convert light into high-bandwidth channels and cellular-scale images, enabling real-time diagnostics, deep space observations, and secure data transmission. The implications touch theory, experiment, and daily life. In this exploration, light spoke back as the universe's language. Photons carry information across space and time, letting us read the stories written in atoms and galaxies. Spectral lines tell us which elements blaze in the heart of a star. Redshift traces the expansion of the cosmos. Interference, polarization, and timing reveal the quantum and relativistic layers underneath everyday glow. Where you stand right now, light is already talking to you. The sunset's colors, the glow of a screen, the shimmer of a raindrop on a lamp post, each a small syllable in the vast lexicon of the cosmos. If this viewpoint felt connected, consider joining the conversation. Subscribe for more journeys through light, and share in the comments which color or photon moment made you pause today. Next time, we'll push further into the invisible edges of light, infrared and ultraviolet, polarization and time-resolved measurements, and we'll offer simple experiments you can try to hear light speaking for yourself.